it does converge, so the sequence of partial sums still converges, but it is not absolutely convergent. So which means, of course, that the series of absolute values has to diverge to plus infinity. Okay, oops, what's happening? Okay. Let me make a few notes about this. I mean, all of you know that if a series is convergent, then the sequence of the AN also has to converge as a sequence. What's more interesting is the next observation, because this will be used a little bit in the discussion later on. If you have a conditionally convergent series, then if you just look at the positive terms, so the n such that an is bigger than 0, and you take the sum over these an, this sum must be plus infinity. And if you take the sum over the negative terms, that must diverge to minus infinity. This is very easy to see. In particular, and that's what I will use later, this is an immediate consequence of this fact. If you have a conditionally convergent series, then it has a divergent subseries. So you can always make, actually can make many divergent subseries. Of course, you can just take the divergent subseries of the positive terms or the negative terms. I mean, this would be divergent subseries. But there are many other divergent subseries. There are also divergent subseries which do not diverge to plus or minus infinity, but which diverge by oscillation. I mean, there are many options. Okay, the next thing I will recall is something which you learn in a first semester as an undergraduate student in an analysis course. So suppose you have a conditionally convergent series, AN, and you have an arbitrary real number, and actually we can also include your plus and minus infinity. Then there's a rearrangement of the series which converges to this given number R, where, of course, if R is plus or minus infinity, I mean by that it diverges to plus or minus infinity. And the rearrangement is given by a permutation. So I write sim omega for the symmetric group on omega, the group of permutations on omega. And rearrangement then just means I rearrange the terms of the series by this permutation. So instead of summing over an, I sum over a pi n. Okay, this is a classical theorem. And also, just let me mention this. We do not just to some other real number or to divergence to plus minus infinity, but we can also get divergence by oscillation, actually. So if you can always find a permutation such that the sum of partial terms, I mean the series a pi n, diverges by oscillation. This means, oops, sorry, let me just recall what I mean by divergence by oscillation. It means that if you look at the sequence of partial sums, so this is the sequence of partial sums, is strictly smaller than its lim sum, than its lim sup. Where, of course, either of these, I mean, this one can be minus infinity and that one can also be plus infinity. That's also an option. It's just the case where there is strict inequality. So this is different from the case where we have convergence or where we have divergence to plus or minus infinity. In these cases here, we would have equality. Okay, now let's see. Using Riemann's rearrangement theorem and using the fact I mentioned before, I will now define two cardinal numbers, It's the so-called rearrangement number. It's the minimal size of a family of permutation such that for every conditionally convergent series, there is a member in permutation in this family such that the rearranged series does not converge to the original value. I have to be a little bit clear about what this means here. Here on the right-hand side, of course, because that's conditionally convergent, this one converges. I'm not saying anything about the left-hand side. I just say it's different. So it can be a different real number. It can be plus or minus infinity, or it can diverge by oscillation. All of these cases are included in this shorthand writing on the left-hand side. Okay, so of course by Riemann's rearrangement theorem that makes sense. I mean, given any conditional convergence series, we have some permutation which does the job. So we can look at the minimal size of a family of permutations which work such that for every conditional convergence series one of them works. And it's quite an easy observation. So this has to be less or equal than the size of continuum, the size of sim omega, which is continuum. And it has to be uncountable, which can be proved rather easily, but there are actually better bounds. I mean, I will come back to this in a minute. The next number is the sub-series number. It has a very similar definition. So what's the difference? This time, for the rearrangement numbers, we asked about divergence or whatever of rearrangements. Now we ask about divergence of sub-series. So it's the minimal size of a family of subsets of the natural numbers omega, such that for every conditionally convergent series, there is a set, there is this infinite subset of omega in this family, such that the corresponding sub-series diverges. And by the observation I made before, given any conditionally convergent series, there is indeed such an infinite subset. It just can look at the positive terms or at the negative terms.
Don't forget that beta is true.
Oh, sorry. Yeah. Oh, sorry. I should have said this. So this is double R, and this one is double S. So it's a German double S. I don't know. This is not my notation. Somebody, I don't know. Maybe Paul knows. Who started the double S? Do you know? You know who invented the double S? Joel, probably. Anyway, I think there have been some complaints about this because this is sort of difficult to read. I think in the referee report of some paper we got some complaints. But anyway, it's a double S. So we have double R and double S. And why is it double R and double S? I mean, the R comes from rearrangement and the S comes from sub-series, and it's double simply because there is already a number called R and there is already a number called S, and they are different numbers. So they will come up again during the talk, actually.
You already said this question. Is divergence Borel or not? Seriously, converge. Is it properly single on
Borel, yeah, sure.
You say there is a limit.
Oh, yeah, sure. Yeah. Cauchy sequence, yeah, sure. Yeah.
See how much analysis I took out?
Okay. Before coming to some interesting questions, let me just make, let me just give some known upper and lower bounds of these two cardinals which we define. So first, let's look at an upper bound. So what do I mean by bounds? We have these two cardinal numbers. We even don't know whether they, a priori, we even don't know whether they are equal or not, or which one is on. And now we want to compare them to other cardinals, which have been studied before. So one of them is non-meager, and that's simply the least size of a non-meager set of real numbers. And it turns out that both of these cardinals are less or equal than non-meager. That's actually has a very easy to present the idea. And this is an old, well, at least for R, it's a very old result. I think it goes back to the 40s. It was observed. I don't even remember by whom, but This has been known a long time ago. So let us assume, let's look at a conditional convergence sequence, conditional convergence series, just one, and also assume we are given some natural number k. Now we look at the collection of all permutations of omega such that there is some number n0 such that the partial sum up to n0 of the permuted series, so it's just a finite partial sum, such that this is bigger than k. This is an open-dense set. Now, of course, I should say what the topological space here is as a topological space. Simply, the topology inherits from omega to the omega. So basically, on omega, you have the discrete topology, and then you have the product topology. And and why is this true? I mean, suppose you are given a finite partial permutation, then you can extend this finite partial permutation again by a finite part, so that if you look at this longer finite part, this sum is bigger than any given number k. And the reason is, by what I observed before, that if you have a conditionally convergent series, then if you sum over the positive terms, this sum must be plus infinity. It must diverge to plus infinity. So what I'm saying here is you just have a finite partial permutation, and then on top of this, you stack finitely many positive terms. If you stack enough of them on top, then you get bigger than k, no problem. Of course, the same is true with minus k, with less than minus k instead of bigger than k. And therefore, what we get is that the collection of all permutations, such that for this particular given series, the rearranged series diverges by oscillation is the density delta. Okay, but what does this mean? It means that if we have a non-meager set of permutations, so now we look at this topology of sim omega, and there we take a non-meager set. This non-meager set, because it's non-meager, it must hit the density delta. So if you have a non-meager set of permutations, it's a witness for this cardinal double R. So just take a non-meager set of permutations. And that also has the property of R, double R is the mean, so that immediately gives this proof. And for double S, the proof is similar. So I leave this as an exercise. Okay, now the question is this upper bound strict? I will come back to this in a couple of minutes. That's a natural question, because it could still be the case that one of these cardinals is simply equal to non-meager. Okay, now we look at lower bounds. Let me just recall the definition of some cardinal invariants of a continuum. The first is B, the unbounding number. It's the smallest size of a family of functions from omega to omega in the Baire space, such that for every function there is one in the family which is infinitely often above the given function. That's the unbounding number. The next one is the splitting number. It's the smallest size of a splitting family, and here we say that a set X splits a set Y if X splits Y into two infinite. Intersected Y must be infinite, but also Y minus X must be infinite. So this is the splitting phenomenon, and then S is defined as the minimal size of a family of subsets of the natural numbers omega, such that for every infinite subset of omega, there is an X in this family which splits the given object. Okay, and finally, covering of null is the least size of a family of null sets covering the real numbers. Okay, and now we get lower bounds, but we have two cardinals, so this is a bit tricky. B is a lower bound for double R. The proof is actually not very difficult, but since I focus on open questions, let me not say anything about that. S is a double bound of double S, So this looks funny because we have S and double S, but that's just an accident. I mean, there is no purpose. The last one is covering null is a lower bound for both, actually. So we have a number of cardinals now, so it's probably better to draw a diagram at that point. So for those, we have non-meager on top, and then we have this double R, and we have S, and covering null was a lower bound for both lower bounds. Now, since the lower bounds are independent, all of these inequalities are consistently strict. So none of these here is equal in ZFC. That's what I'm saying. And the reason is simply because it's already known that for these three cardinals, they are independent, in the sense that for any two of these three cardinals, any order is consistent. So it's consistent that B is less than S, it's consistent that S is less than B, and so on. And that then gives immediately that there are models where B is strictly less than double R, and so on. Okay, so for the lower bounds, in a sense, we have no question. For the upper bound, we still do not know whether it is strict. However, there is one known consistency result, and this is that double S is Aleph 1 in the label model. This is actually quite technical. It involves some work. I mean, it's done roughly in the following way. One defines a relative of S, which is bigger than S, and consistently strictly bigger, and shows that this relative of S is an upper bound of double S, and then one shows that this relative of S is Aleph 1 in the label model. The label model is one of the canonical model where the continuum hypothesis fails, where continuum is Aleph 2, and it's sort of the canonical model for B for the unbounding number being Aleph 2. So it's a minimum model where the unbounding number is Aleph 2. So immediately we get as a consequence that it's consistent that double S is less than B, and so it's also consistent that double S is less than double R, and it's consistent that double S is less than non-meager. So we have a model, let's see. This is the label model. I mean, if you look at this diagram, we would split the diagram like this. So all of these cardinals are big. They are Aleph 2 and equal to continuum, and these three are Aleph 1. And so we have in particular the consistency that this one is smaller than any of those. So in particular, this is not a lower bound over there, even though it's a lower bound here. And also we know something about these two new cardinals. This one can be less than that one. Okay. But unfortunately, we do not know the other way around. And the best you could hope for is, you see, these are lower bounds for double R, but it's not clear whether S is a lower bound. So if we can show that it's consistent that double R is less than S, this would split the diagram like that and would solve all the other questions. That would be the best result. I conjecture this to be true, and there is a canonical, I mean, there's a standard model you would want to look at. This is the so-called Blastula model. It's a model where B is less than S. Well, there are several models where B is less than S, but there is a reason for looking at that one. The reason is that R, which I haven't defined yet, is also small in this model, and that may help somehow to do something with double R. So I do conjecture this is true, but I don't really know. So that's my conjecture about this. Even if this is not true, so even if S is strictly less or equal than double R in ZFC, we can still ask weaker questions. You can ask for the consistency of double R less than double S here, or at least for the consistency of double R less than non-meager. So you see, all of these are not known. It's not really known what the relationship of this one between any of these three is. For all we know, that one could even still be equal to non-meager. So I very strongly conjecture that's not the case. Okay, so that's my first question. Now let us look at some variations of these cardinals. double Ri has a very similar definition than the rearrangement number double R. But now we ask for convergence to or divergence to plus minus infinity. So double Ri is the minimal size of a family of permutations such that for every conditionally convergent series there is a permutation in this family such that the rearranged series converges to plus or minus infinity. Okay, let's just do the same thing with double S. Double S is the minimal size of a family of subsets of omega, such that for every conditionally convergent series there is a set in this family such that the corresponding subseries converges to plus minus infinity. Clearly, double R is less or equal than double Ri and double S I. The I stands for infinity here because we have plus minus infinity. That's obvious because here we ask for something, we are more restrictive. For double R we just ask that this series does not converge to the original value, which was a finite value. So it could either converge to a different finite number, it could diverge to plus minus infinity like here, or it could diverge by oscillation. So there are like three options. And now we just focus on one of these three options. Okay, and again, of course, you can ask, maybe these cardinals are simply equal, but actually it turns out they are not. And the reason is the following. For explaining this, I need two more cardinals, the dominating number, that's the smallest size of a dominating family in Baire space omega to the omega. So the smallest size of a family of functions such that for every function there is one function which is above it from some point onwards. And covering meagre is the least size of a family of meagre sets covering the reals. That, of course, has a similar definition like covering null, which I defined before. And now we can see that D is less or equal than double Ri, and also covering meagre is less or equal than double Si. Again, these are not very difficult proofs. Let me see. So now I think the diagram gets a little bit difficult now if I continue drawing this. Covering meagre, I should of course say that covering meagre is actually below D. So this is below D, and then we get double Si and double Ri is even above this one. And here, of course, we have these relationships. Okay. Well, there are some other relations. For example, D is above S, and D is above B, so there are some more. There is this one, and there is this one. But that's not important. I mean, the important thing I want to stress is just that these are lower bounds for these two cardinals. And then, of course, we can see that these are strictly larger than the ones on this side. And the point is simply we can use the Coulomb model, which is the simplest model for the negation of the continuum hypothesis. The reason is that in the Coulomb model, covering non-meagre is R left 1 and covering meagre is R left 2. So everything here is R left 2 and everything there is R left 1. Because here the upper bound is R left 1 and there the lower bound is R left 2. So the diagram is split like this. So that would be the Coulomb model. Okay, that's not very interesting. This was sort of a side remark. What I really want to focus on is how big these cardinals, these two cardinals on the right-hand side are. And there are no known upper bounds for these cardinals in ZFC, except, of course, for the size of the continuum. It's consistent that double Ri is less than the continuum. How is that proved? Basically do the following. You use a C, and there's a CC forcing, which adds a permutation such that for all ground model conditional convergence series, the rearranged series either diverges to either plus minus infinity. You can construct such a forcing. This is not completely trivial. You do it in several steps, I mean, but there is basically a sigma-centered forcing doing this job. And then once you have this forcing, what you do is you start with a model where the continuum is large, and you iterate this forcing for Aleph1 many steps, and then you get a model where this cardinal is Aleph1 and the continuum is still large. Fine, so this is easy. But what about having the other one, this cardinal less than continuum? I don't know. I don't know how to do this, and it's actually not clear. It may also be simply that this is equal to continuum, but we don't have a proof for either. We don't have a proof it's equal to continuum, we don't have a consistency proof. Now, of course, for a consistency proof, you would want to do something like that, and what we do know is that this is not possible. So you can't add a subset of omega such that for all ground model conditional convergence series, the subseries diverges either to plus minus infinity. You can't even do it for 4. So this is actually a ZFC thing. I mean, if you can construct 4 conditional convergent series such that there is no subset which works for all 4 of them. Of course, this is some hint that the cardinal should be continuum, but it's actually not quite, it's not quite enough, because it could still be the case that instead of adding one subset, we could add countably many subsets, such that they work for everybody of the ground model. That's not ruled out, and that would be sort of the approach to take if you want to show consistency, or we have to show that they are equal. Okay, any questions so far?
What was that 4? I didn't understand.
Oh, the 4 was simply, you can, so even for 4 you cannot do that. Even for 4, for 4 series, for 4 conditional convergent series, you can't do that. It means that there are 4 conditional, you can construct 4 conditionally convergent series such that there is no subset of omega such that all of them for this subset, all of them simultaneously diverge to either plus minus infinity. 4 is the minimum, right? It works for 3, right? Yeah. Okay. Actually, sorry, when did I start, Vera? You know how much? Sorry? Till 10:05. Okay, thanks. Okay. So because I have 2 more sections, I have 20 minutes. I should do each section in like 10 minutes. But they are shorter than the previous section, so I think I will be fine. The next section is about Borel versions of cardinal, some cardinal invariants. What I mean by Borel versions will be clear in a minute. This is actually spread over several papers, at least 3 papers with Yuri, Dilip, and Vera. Okay, let's recall the almost disjointness numbers. I think all of you have heard about almost disjoint families and mad families of subsets of the natural numbers omega. Now, A, the almost disjointness number, is the smallest size of an infinite mad family. So mad means maximal almost disjoint. Almost disjoint family they are both infinite, but they have finite intersection. Maximal almost disjoint means it's maximal with this property. And we have to add infinite here because, of course, they are finite mad families. They are sort of the trivial objects. But if we look at infinite ones, then we get a cardinal number. This has to, again, it has to be an uncountable cardinal, which is, of course, less or equal than the continuum. Now we come to a variation of this cardinal, A closed. So what do we do here? Instead of looking at an infinite mat, we look at an infinite family of closed subsets of omega to the omega, such that their union is a mat family. So of course, each of these closed sets is an almost disjoint family, and if you take all these almost disjoint families, all these closed almost disjoint families together, you get a mat family. You just take the union. And you ask for the smallest size of such a family of closed sets. And the next one is very similar in definition. Instead of asking for closed, we ask for Borel. So we ask for an infinite family of Borel subsets of omega to the omega, such that their union is a maximal almost disjoint family. So of course, again, each of these Borel sets must be an almost disjoint family. Then clearly, just by the definition, we get A Borel less or equal than A closed, less or equal than A. I should also say, I should say something about why these cardinals are non-trivial. That's an old result of Matthias, and that says that a maximal almost disjoint family, a Mat family, can never be Borel, or even analytic. The least complexity a Mat family can have is co-analytic. So it cannot be Borel, and therefore this cardinal has to be at least Aleph 1, obviously, because you need, if you have countably many Borel sets, the union is again Borel, so that's silly. So you need at least Aleph 1 mainly. And of course, again, you can ask whether these cardinals are equal. So what's known about this? First, let me look at some bounds for these cardinals. Let me recall the tower number, the least size of a tower in omega to the omega. So a tower is a decreasing family in p omega mod fin. It's decreasing by inclusion mod finite, and there is no infinite subset of omega which is almost contained in all of the members of the tower. So it's decreasing and maximal in a sense. It cannot be extended. Okay, so a lower bound for A is B. That's a classical result, which has a very easy proof. A lower bound for A Borel is T. So that's of course T is less or equal than B. So this lower bound is not so good, of course. So we have here T and B, and we have A, and here we would have A Borel, and then here we have A closed. That's what we have so far. Some more results. They are not immediately connected with the questions here. Well, in a sense, they are actually. So D equals Aleph 1 implies that A closed is Aleph 1. It's a result of Ragavan and Schellach. The next one is A Borel. It's consistent that A Borel is bigger than D, so that one can be bigger than that one. So there is a model which splits this diagram like that. And this is done by, like Schellach's proof for the consistency. Schellach proved the consistency of A bigger than B, like many years ago in the 80s. Modifying this, we also get that one. So that's not so difficult. A deeper result by Ragavan Schellach is the consistency of A Borel bigger than D. Here, this has some LC, so this involves large cardinals, I think. You need super compact, at least one super compact or more. Of course, this is all CCC forcing, but they work with Boolean ultra powers of forcing notions. For doing a Boolean ultra power, you need the super compact cardinal. Of course, this is a better result than that one because D is above B. But this model, actually, you have B Aleph 1 and A Borel Aleph 2, so they are small cardinals. That's not possible here because if this one is Aleph 1, then that one is also Aleph 1 by this result. So they have here the continuum has to be at least Aleph 3, but actually in their model, of course, the continuum is really big because it's above the super compact. I mean, there was a super compact which is not super compact anymore, but yes.
In the usual template, what's the value of A Borel?
Good question. We don't know, and the reason we don't know is probably no. Actually, we know it's Aleph 1. It must be Aleph 1. If you use the one with Heckler forcing, and the reason is the following. I will come back to that. Basically, the thing is, you see, here we don't have, so why does the other proof not work? The other proof depends on the fact that we have this inequality. Because the template model makes B large enough, and then A has to be even larger, and that's why you get this. But this B is not a lower bound of that one, and actually, if S is R, that's not quite true. It's actually an open question, but it's almost true that if S is Aleph 1, then this one is also Aleph 1. And in the template model, S is Aleph 1. Something a little bit stronger than that is enough, and that little bit stronger will be true in the template model, and for that reason, this will be Aleph 1. A closed is Aleph 1 in the Heckler model. The Heckler model is one of the standard models making B large. So what this gives us is the consistency of A closed less than B, and therefore also less than this one. So we can split the diagram like that. So in particular, these two cardinals, before we had these three cardinals, it wasn't clear whether they were equal. At least these two we can separate. And that was actually the motivation for defining these cardinals. Well, the motivation was some definability problems, which I'm not going into. But I wouldn't define these things like if you a priori, because you would think maybe they are just equal, but we actually realized they can be different. That made this interesting. Okay, now we come to problems. Let me just record the distributivity number H. It's the smallest size of a family of dense open sets in P omega mod fin, such the intersection is not dense. By homogeneity, here we can also ask for the intersection to be empty. It would be the same. That doesn't make a difference. So there are several questions about this. The first one is, does S equals omega 1 imply A closed is omega 1? That's what I just mentioned concerning Osvaldo's question. You see, this is almost true. Actually, let me just continue this, because I wrote this here at the bottom. Slightly weaker statement than this one is true, we know that. So we have a little bit a strengthening of S equals omega 1, basically having a sequence which is eventually splitting of size length omega 1, something like that, a little bit stronger than that. That's enough to get A closed equals omega 1, and that actually is sort of, we discovered that only later, but that's used in both of the theorems, in two of the theorems I discussed before, namely the proof that A closed is Aleph 1 in the Heckler model, and also the proof that D equals omega 1 implies A closed is Aleph 1. I mean, both of these proofs are based on they follow from the same combinatorics. There's one basic combinatorics which can prove both. And the basic combinatorics is about saying basically something a little bit stronger than S equals omega 1 implies A closed equals omega 1. And then this is still true in the Heckler model, so we get this. And this also implies, this is still a statement which is much stronger than D equals Aleph 1. Okay. Oh, sorry, which is, yeah. Sorry, which is weaker than D equals Aleph 1. It's still weaker than D equals Aleph 1. Another question would be A Borel bigger or equal than H. That would be natural given Matthias's theorem, but we don't know. What I'm really and maybe they are. I mean, it looks plausible, but I have no idea how to prove it. But also, there is absolutely no idea on how to separate them. Okay, now we come to another cardinal where we redo the same game, namely the independence number. It's the smallest size of a maximal independent family is the independence number. And independent means that, okay, we have a family of subsets of omega, and any finite Boolean combination is infinite. So you take finitely many of your family, intersect them. You take finitely many, another finite set, and you intersect the complements, and you intersect these two sets, and this still has to be infinite. So any finite Boolean combination must be infinite. Now, of course, okay, we can just do the same thing like we did before for A. We can define I closed and I Borel. So instead of asking for maximal independent family, we ask for a family of closed subsets of omega to the omega such that their union is a maximal independent family. So of course, each of these closed sets must also be independent, and so on. And similarly for Borel, again, we get this obvious inequality, and we can again ask whether these cardinals are equal. Now, unlike for the situation here, I actually know nothing about this question. So that's really, but I find it interesting. So what is known about lower bounds? Let me recall the reaping number. It's a dual of the splitting number. It's the smaller size of a family of infinite subsets of omega, such that for every subset you get a member in this family which is either almost contained or almost disjoint from the given set. And now we have three well-known lower bounds for I. One is R, one is D, and one is non-meager. The other two cardinals were already defined. We do not know whether any of these is a lower bound for I closed or I Borel. The best lower bound we have for I Borel is covering meager. I already mentioned covering meager is below D, so this is not as good. This is not as good as this lower bound. Covering meager actually is also below R, so both of these lower bounds are of course better than this lower bound. And result, Jonathan told me, I compact, so you can replace closed by compact and you get a cardinal, which is of course, it must be somewhere in between. I'm not sure whether it's equal to closed in general. This is still bigger than D. It's basically the same proof, and then it follows that this must be equal to the max of D and I Borel. Okay, so what's the question? The question, of course, is whether these three cardinals are simply equal. I closed and I Borel. And alternatively, you may ask whether it's consistent that I closed is either of these cardinals is less than maybe, well, sorry, I closed is less than D or less than R, less than non-meager. Of course, either of these consistency results would solve this question in the negative. So either we have to make a ZFC proof they are equal, or we have to show this is less than I, but showing this is less than I, of course, the approach would be to show that it's actually even less than one of the well-known lower bounds of I. That would be the approach. Okay. I have like 5 minutes left, I guess, right? So this will be very quick for the last section. Game versions of cardinal invariants. That's just one paper with Michael and Victor, who is also here. So let's see. There are actually 3 more cardinals now, and all of them are related to known cardinals. The first one, we look at games. And the first game is the so-called tower game. This is the game, the best understood of the 3 games, actually. So, there are 2 players called builder and spoiler, and they play a decreasing sequence, decreasing by almost inclusion, sequence of subsets of omega, and they are called X alpha, and the length of the play is beta. Beta is some ordinal. Okay, so, and let's also fix it, that's important for what comes. Builder plays at even steps and spoiler plays at odd steps. So the game looks like 0, then spoiler plays x1, which is almost contained in x0, so it's contained mod finite, then builder plays x2, again almost contained x1, and so on. And they play, and it's an infinite game, it's a transfinite game. Okay, and now builder wins the game if what we get out here is a tower. Now recall what a tower is, I explained this before. It's a decreasing sequence in P omega mod fin, which has nothing below. So it's maximal. So there is, tower means there is no infinite subset of omega which is almost contained in all of the X alpha. And if it's not a tower, then spoiler wins. And now let P builder is the minimal ordinal beta, such that builder has a winning strategy in this game. This is defined as an ordinal a priori. However, it's not too difficult to show that this is actually a regular cardinal. So that one we know. And now we look at bounds for this. Of course, T is a lower bound. because T builder, if he has a winning strategy, he builds a tower, so this has to have a size least T. And H, the distributivity is an upper bound, because basically from the distributivity we get the base matrix tree, and from the base tree we get a strategy. Another result is that the diamond not equal, this is a Borel version of this Devlin-Schellach diamond. That implies that T builder is Aleph 1. So it's consistent that T is less than T builder, and it's also consistent that T can be consistently strict, and the proof is, for one, it's an iteration of labor forcing with an appropriate filter. So what you do is basically you start with some tower and you say, okay, we preserve this tower, and then you do an iteration destroying all possible strategies. And you can do that while preserving the tower and with a somewhat sophisticated labor forcing with a filter. But it's all CCC. The model for the second one is the Matthias model. And the reason is simply it's well known the Matthias model satisfies the diamond. So the diamond is true, so T build is omega 1. On the other hand, it's also well known that the Aleph 2, it's sort of the standard model for H being Aleph 2. So we get this consistency. Okay, there are some questions about this tower game too, but they are sort of more specialized. So let me rather look at some other games. So this was simply just for motivation, sort of. The next one is the ultrafilter game. This time we play a filter base, and again, builder is in the even runs, spoiler is in the odd runs, and we play a filter base, and builder wins if what comes out is an ultrafilter base. And U builder is the minimal beta such that builder has a winning strategy in this game. With this definition, we even don't know whether this is a cardinal. I mean, it should be a cardinal, but a priori it's only defined as an ordinal. And of course, there is a related cardinal, that's the ultrafilter number. It's the smallest size of an ultrafilter base. Clearly, U, this ultrafilter number, is a lower bound of U builder. Then there's again a diamond result. The diamond for the reaping number R implies U builder is omega 1. And we also know it's consistent that this U is strictly less than U builder. But here we even don't know it's a cardinal. And there are some other questions about that. I come to my last slide now, so I have like 1 minute maybe. Just one more game, and it's basically the same thing, except that now we play almost disjoint family. Before we played a filter base, now we play an almost disjoint family. The rules are the same. The X alpha builder plays in even runs, spoiler in odd runs, and the X alpha have to be almost disjoint, and builder wins if a mat family is played, and A builder is the minimal size, the minimal length beta, such that builder has a winning strategy in the beta length game. Again, you can ask whether it's a cardinal, which should be true, but we don't know how to prove that. And we know, of course, it's clear that A builder is bigger or equal than the almost disjointness number A. I should have said, of course, this has to be infinite. I mean, beta has to be an infinite ordinal. And delta diamond of B implies that A builder is omega 1. So again, we get a diamond result. Here we don't even know whether A builder can be bigger than A, so that's one more question. And that's all. Thank you very much.